All right, everyone, we had a little bit of homework last night on page 255, both involving, or all three of those questions involving centripetal acceleration. We talked about this over the last 2 days now. When an object moves in a circle with uniform circular motion, it's going at a constant speed. But just because it's going at a constant speed doesn't mean it's going at a constant velocity. Acceleration is dependent upon the change not in speed, but the change in velocity. So since the direction of the object going in a circle is changing, the speed doesn't have to. Speed remains constant in uniform circular motion, but direction changes. And as long as the direction changes, the velocity changes. And as long as the velocity changes, there's an acceleration. We can find the magnitude of that acceleration, which, by the way, points toward the center of the circle. We can find its magnitude with a new equation that we learned 2 days ago. A is equal to v squared over r. Centripetal acceleration, v squared over r. Notice the absolute value sign around it. We're not going to get the direction out of this equation. It's a vector. It has a direction, but the equation doesn't tell us what the direction is, hence the absolute value sign. That's okay. We don't need the direction because we know which direction it's pointing, always pointing toward the center of the circle. So this equation is going to allow us to get the centripetal acceleration. Sometimes we don't have the value of v. If we need the value of v, how might we find it? There's another equation that we learned to find v. Good. V is equal to 2 pi r over t. R stands for the radius of the circle, right from the center to the outside, and t stands for what? Kevin, what does t stand for? That big T then. You're almost there. Not the revolutions per second. Yep. The time it takes for one revolution. So instead of the revolutions per second, it would be the seconds per revolution. Okay, the time for one complete revolution. The period, right? 2 pi r, 2 times the pi times the radius over the period. So those are the combinations that we have to use for one or all of these questions here. Any of these that we need to go over, 1, 2, or 3? Yep. 2. Yeah, 3, 2 and 3. All right, 2 and 3 it is. 2 says a child playing with a top. You guys know what a top is? Like, you don't see those toys really anymore now, but one of those things where it's kind of like this bowl-shaped thing with a kind of a point on the bottom. You push down on something and it spins it around, and then it spins on this pointy thing. Okay. So this child playing with a top spins it so that it has a centripetal acceleration of 125 meters per second squared, about 12 Gs. This is at the edge, which is about 3 centimeters from the axis of rotation. So if this is the top, looking at it from above, this would be the center, the axis of rotation. This distance right here is 3 centimeters, or 0.030 meters. That means r is going to be 0.0300 meters, and a centripetal acceleration is 125 meters per second squared. What's the speed? Well, we're going to say a is equal to v squared over r, right? Well, we're looking for v. So the r goes up by multiplying. It becomes a times r equals v squared. And then I got to get rid of the squared. How am I going to do that? Bart, how am I going to get rid of the squared then? Right. So v becomes the square root of a times r. So it's the square root of 125 times 0.03. And when I do that math, I should, I think, get 4.57 times 10 to the 2, or 457 meters per second. 1.94, meters per second. Yeah, you know what, actually? You stop and think about that. The edge of this toy moving 457 meters per second, 1.5 times the speed of sound? Yeah, probably not. 1.94 sounds a lot better, actually. That's why we should always, every answer we get, we should always stop and think, is it reasonable? Does it seem to make sense? 1.94 makes way more sense. Right? Hey, what's the direction of the acceleration? We're not told that, are we? Well, we kind of are. What does the word centripetal mean? Yep. Towards the center. So the acceleration is, in fact, toward the center of the circle. All right, let's take a look at number 3. says a helicopter blade has a diameter, be careful there, don't like that word diameter. I'm used to using what word that's like diameter, but not quite the same thing. Radius. And radius is half the diameter, right? So if we've got a diameter of 14 meters, that means that R is going to be 7 meters. The acceleration, we're told, is 25, 27. And we're looking for the period of the helicopter blade. We're looking for how long it takes the helicopter blade to make one revolution. We don't know what that time is. I don't even know what it is off the top of my head, but we could predict probably that it's going to be pretty small, right? You see those helicopter blades moving, you know that they're moving pretty fast, and it doesn't take very long to go all the way around the circle once. Okay, ideas. Everybody should have a place to start. It may not be the same place. That's okay. Everybody should have a place to start. Okay, let's see here. Derek, where's your place to start this question? Okay. Centripetal acceleration is A is equal to V squared over R. Brian, is that a valid equation here? All right, good. Then that's a good place to start. It may not be the same place to start as somebody else used. Anybody else start somewhere different? Anybody start with V is equal to 2 pi R over T? Anybody do that one first? Yes, Stephanie? Okay. So Derek started with this equation. Stephanie started with this one. Jacob, is that a valid equation for this problem? Sure it is. Do we know for sure we're going to use both of them? Well, some of us know for sure because we can kind of see a couple steps down the road. Some of us don't know for sure. That's okay. They're both valid equations. Okay, try one of them. I don't care which one you try first. Derek was first to give it to me, so we're going to start with A is equal to V squared over R. Okay, but in the end, okay, Stephanie starts with this one, just as good. Okay, they're valid equations. Everybody should have a place to start, whether it's this one or this one. All right, centripetal acceleration, we've got A, we've got R, we don't know what V is, so let's solve for V. Now, V is not what we're looking for, but that's okay. I never want you to be afraid of not being able to solve what you're looking for right away. Get something. Get V. Maybe it's helpful, maybe it's not helpful, so what? Just get it, and then hopefully it will help me down the road. If it doesn't, then, oh well, you just wasted 30 seconds of your life, and I know never getting that back, that 30 seconds of your life back, but it's not the end of the world. Okay, if you've done something you didn't need to do. So we get 2527 times R, 7.00 meters. Remember, not 14, but 7. Derek, what'd you get there for speed? 133. Let's go a couple more decimals. Okay, exactly. Thank you. 133 meters per second. Final answer, no. But you know what? Even if Derek doesn't know where to go with it from here, he still gets part marks, right? Because he's done something that's correct. Now, if he does know where to go with it, he's going to go to where Stephanie suggested that we try first. And that's V is equal to 2 pi R over T. Rearrange that to solve for T. The V comes down, the T goes up. It becomes 2 pi R over V. So we got the number for pi, 3.14. R is 7, and V is 133. We do the math there, and it works out to be 0.331. Done. Derek's method worked. Now, Stephanie started with T is equal to 2. You didn't. Okay, well, let's pretend you did then, Stephanie. So Stephanie started with T is equal to 2 pi R over V. And then she realized when she started plugging numbers in, oh, wait, I don't know what V is. So it wasn't helpful. That's okay. Try something else. Then she stumbles upon this equation that Derek tried first. She gets the value of V. Oh, wait, I already have that equation. Now all I have to do is plug that value that I just solved for into T is equal to 2 pi R over V. Good there? Let's try this one. This one says determine the centripetal, not acceleration, but centripetal force. Generally, these problems aren't any harder than the ones we just did because force is just m times v squared over r. Centripetal force exerted by the rim on a dragster's wheel on a 45 kilogram tire. The tire has a 0.480 meter radius and rotating at a speed of 30 meters per second. Here's my mass. Here's my radius. They're making this question too easy. Here's my speed. We're looking for the centripetal force. Well, we know that the magnitude of it is mv squared over r. Oh, wait. Look at this a second. We're looking for the force, right? Not the speed. Oh, this is a harder question than I thought. All right, that's okay. I don't know what v is. Whatever shall I do to find v? Seth, you got an idea there? Any ideas to find v? Okay, so Seth says A is equal to V squared over R, a perfectly valid equation. Now, it's not, oh, that's speed. Yeah, no, we already have that. You're right. Boy, oh boy, we're trying to make this harder than we have to, eh? Yeah, we got the speed. Seth's looking at it like, Seth's probably looking at me like I got a hole in the head thinking like, no, we already have it, but he wouldn't be asking me if we already had it. Let's say we didn't have it, but we had something else given to us, okay? So I asked Seth, what would you use to solve for V? Seth said A is equal to V squared over R. Honestly, Seth, that, even if the question was phrased a little bit differently, that one probably wouldn't have worked. Probably wouldn't have worked. And the reason it probably wouldn't have worked is because that equation is basically in this one already, right? F is m times A and V squared over R, right? But that's okay, okay? What I want everybody to understand, including you, is that you came up with a valid equation there. A is equal to V squared over R describes this situation. If you find that it doesn't work for you, then what do? Try something else, right? As long as you're trying valid things, it's okay if it's not the one that's going to work for you. So as it turned out, we didn't need to solve for speed at all because we already had it. If you did, we probably would have went with V is equal to 2 pi r over t if we did need to solve for it. All right, so we got the value of V, 30 meters per second. Thanks to Haley, again, for making me feel inadequate and making mistakes all over the place and announcing it to everybody. 45 times 30 squared divided by 0.480. Let's figure out what that is. Good question, Lewis. Lewis said, shouldn't we say V squared over R, like say 45 times 30 squared over 0.480? Get this number and then multiply by 45. Is that what your question is? Okay. Yes, you should do that. Or you should do this. Because in the end, 30 squared divided by 0.48 times by 45 is the same as 30 squared times 45 divided by 0.48. So it doesn't matter what we do it in. That's a great question because the way that I usually write the equation is m times v squared over r, not v squared over r. But they both mean exactly the same thing. So it doesn't matter which way you do it. Okay? So why do I write it like this? Well, because it comes down to where that equation comes from. F is equal to m times a. M times a. Well, a is v squared over r. So that's the reason I usually write it like that, but it doesn't matter. Good question. Yeah. Okay, what is it? 84,375. Thank you. How many digits should we round that to? 1, 2, 3, 4. Allie, how many digits should this example be rounded to? Good. 3 digits, 3 digits, 3 digits. We're going to say it's 8.44 times 10 to the 4 newtons. Now, it only said the magnitude. We didn't need to find the direction here. But if we did need to find the direction, it's not very hard. Right? Which way is the direction here? What's the direction here? Toward the center. Not from the center, but toward the center. Yeah, good. All right, let's try a couple of those questions, okay? Any issues with either of those two questions on 265? 256. I'm getting dyslexic here. 256. Both of them okay? How about the rearranging of question number 2? Let's take a look at that, okay? Even if none of you are owning up to needing a little bit of help on that, we'll do it anyways here. Question 2 says, this pebble that has a mass of 0.0021 kilograms stuck in the wheel of a dirt bike, the radius of the wheel is 23 centimeters, which we're going to want to make meters, 0.230 meters. And we're solving, we have the force here. And we're solving for V. So the equation that I'm going to use, of course, is F is equal to mv squared over r. Somebody asked me this question. What do I get rid of first, the m or the v? What's the answer to that question? Sorry? Yeah. Or the r. Yeah. Yeah, boy, oh boy. It's one of those days. Yeah, it's just one of those days. What do I get rid of first, the m or the r? The m or the r? Yeah. Yeah, it doesn't matter. Like, get rid of what's not attached first. Well, everything's attached, so now get rid of what is attached. It doesn't matter what order you do that in, the m or the r. So let's take the r up by multiplying, although I could have taken the m down by dividing. Be fine. F times r equals mv squared. Take the m down by dividing now. F r over m equals v squared. Now, how to get rid of the squared? Square root it, right? So it becomes, v becomes the square root of f times r over m. The only thing here is we got to recognize that that 23 centimeters is 0.23 meters. How many people made that mistake of forgetting to convert? I know there was some of you. I know it wasn't one person. I know it was more than one of you that forgot that, because that's a common mistake there. Just be careful there. Do that math, we get 8.5 meters per second. Oh, here's an interesting question. What's the maximum speed at which a car can go around a turn of radius 40 meters? If there's a coefficient of friction of 0.60. We say a coefficient of static friction, because that's actually what keeps a car on the road, right, is static friction. Even though the car is moving, we don't want the car sliding, right? Sliding friction is kinetic friction. So if we're not sliding, it's static friction. Coefficient of static friction is 0.60. How fast can we go? This would be useful to know if you're a traffic engineer, you're designing highways, designing roadways. How fast should we set the speed limit at? Any ideas here? Somebody is going to tell me something here. Okay, someone's going to tell me something. Okay, I don't care if it gets me the answer. Someone's going to tell me something that's valid here. Kaylin, tell me something that's valid here. Doesn't have to get me the answer, okay? Remember. Okay, you should move somewhere where you can see them, really, seriously. Yeah. Oh, the maximum force of static friction? Okay, good. It's funny, because Jacob just said, let's find the maximum force of static friction. That's actually not what I was thinking of first. That's okay. Okay, what he's thinking of is just as good as what I was thinking of, because that's a valid equation. We're probably going to end up using that now as well, but even if we don't, that's okay. It's still a valid equation. Let's see if we can find its value now, okay? We wrote down the equation. If we can't find its value, all right, then we'll move on and do something else. If we can, then great. 0.60, it's a horizontal surface, so the normal force is going to be m times g. It's 1,500 times 9.81. Somebody calculate that number for me, please. 8,829 newtons. Any decimal places? No? All right, thank you. Now, Jacob, here's the bad news. Bad news. The bad news is that's not even remotely close to a speed. That's a force, right? Not even close to a speed. The good news is maybe we can use that to get the speed. And that's where we find ourselves all the time. We solve for something that we're not looking for, and then we use that to get what we're looking for. I don't even care if we don't end up using this. Has what we've just solved for proven to be wrong? No, it's just not what we're looking for. All right, Jacob's off the hook. Somebody else now tell me something that's valid. Right, Seth? Okay, something that's valid. Okay, perfect. Okay, in fact, I'm glad you gave me that one, actually. Okay, Haley just said, she said, I don't think it's going to give me an answer, but I'm going to write down t is equal to, or v is equal to 2 pi r over t, because it's valid. Is it valid? Is the object going in a circle? Is it moving with a certain speed equal to 2 pi r over t? Absolutely. Now, I agree. I don't think that's going to give you the answer, but I'm not worried about that, okay? I want you guys to be at the point where you try things that are valid. Haley tries this. She tries to find the speed. Hey, 2 times pi times r. She's got that, right? Don't know what t is. Maybe she can find t. I don't think so. If she can, then great. If she can't, then all right, we'll try something else, right? Okay, so f is equal to mv squared over r, and then we rearrange that. Okay, is that valid, guys? Stephanie, is that valid? Absolutely it is. Okay, everything we have up on the board here is perfectly valid. If you listen, if you spot right away that this isn't going to work for you, all right, then don't write it down. That's fine. You don't have to write it down. But it's also okay to write it down. It's not wrong. It's just not helpful. All right. We're solving for v here, right? So let's see if we can rearrange this to solve for v. F times r over m square root. R we have, m we have. What about this F, this centripetal force? Yeah, why can this force, this max force of static friction, be subbed in for centripetal force? What did we say the other day about centripetal force? It is always caused by something. Sometimes it's caused by gravity, sometimes it's caused by an electric force, sometimes it's caused by friction. In this case, it's caused by friction. Listen, if it's caused by static friction, then why wouldn't those two forces be equal? We're going to say 8829 times the radius of 40 divided by the mass of 1500. And then we're going to square root that. Let's figure out what that is on our calculators here. $8,829 times 40. Let's divide that by 1500. Let's square root that. And we get 15.3, or we're going to round that to 2 digits, 15 meters per second. So if you're designing this highway, and this is the setup of the highway, you better make sure you make the speed limit less than 15 meters per second. Or even good drivers are going to be going around this turn and they're going to slide right off the road because friction is not strong enough to hold them on. What's one thing that highway designers will do sometimes when they have to make a corner pretty tight? They slope it, they bank the turn. So then you have friction that's directed toward the center of the circle, but you also have, if you bank that turn like this, usually they're not banked quite that much, but okay, this is your car looking at it from behind. If you bank the turn like this, you have a normal force acting up like this. You have friction acting toward the center of the circle, but you actually have a component of the normal force acting toward the center of the circle as well. That's why when you bank something, it becomes easier to stay in that circle because a component of the normal force is helping you. Does that make sense? That's a more complicated problem. We could do it, but it's a more complicated problem. Does this make sense? All right. Are those ones then, please? All right, let's take a look at question 2 here. It says, automotive manufacturers test the handling ability of a new car design by driving a prototype on a test track of a large circle with a radius of 100 meters at ever-increasing speeds until the car begins to skid. So basically what we're trying to do here is seeing how fast you can go before the coefficient of friction isn't big enough to hold it anymore. So we're going 95 kilometers per hour, and when this one begins to skid, we want to find the coefficient of friction between the car tires and the track. So question number 2, we've got a radius of 100 meters. We've got a mass of 1,200 kilograms. We got a speed of 95 kilometers per hour. Although we know we never want to be in kilometers per hour anymore, we know we want to be in meters per second. So Ryan, what do we got to do to convert that to meters per second? Good. Times it by 1,000 to get meters, divided by 3,600 to get seconds. So it becomes what, Ryan? Thank you. 26.389 meters per second. We're looking for the coefficient of static friction there. Okay, somebody tell me something that is valid here. Ryan, while we're on a roll here, tell me something that's valid. Tell me something that you might want to try. Okay. Okay. So FSF max is equal to mu times the normal force. All right. So, okay, perfectly valid in this situation, right? The only problem is we don't know what mu is. That's what we're looking for. But we also don't know what FSF max is. We don't know what FN is, but we could find that pretty easily by just saying 1,200 times 9.81, right? So, good. Okay, good. My gut feeling is we're going to end up using this. But if not, oh well. It's a valid equation. What else? What else should we try here? What else is valid that might work? Seth? Good, good. Hold on for a second, guys. F is equal to mv squared over r, Seth says. That's the centripetal force. So, look, we can find that. Just don't pack up here, guys. We're not finished. 1,200 times 26.389 meters per second. Square that. Divide it by 100 meters. I'm not sure what we get there. Okay, but when we do get the centripetal force, Seth, what value is that to us? Good. It's the same thing as the maximum force static friction. So now we have this value as well. We also have the normal force because it's just m times g, 1,200 times 9.81. Now we can find mu by saying FSF max divided by Fn, the normal force. We got it. And we get 0.710 meters. We'll take a look at number 3 tomorrow. I know that somebody asked to go over number 3. We'll do that tomorrow, promise. Or if you want to stick around for scheduled help, we can go over that. Okay. Does this make sense, guys? All right. Tomorrow we'll take a look at some problems where we're going in circles that are vertical, like this, okay, which is pretty useful for us for our field trip on Tuesday. Okay, that's it for today, guys. Finish this up if you haven't already, please, for homework, okay?